I'm skeptical of love. So when you hold my hand, do you wanna hold my heart? When you say you want me, is it all of me? Just one part. So when you hold my hand, do you wanna hold my heart? When you say you want me, Mama said there'd be boys like you, tearing my heart in two, doing what you do best, taking me for a ride, telling me pretty little lies. But with you, I can't resist. Maybe Mama doesn't always know best. I'm terrified, but I'll never let you know. Social suicide, if I ever let it show. Everything feels just right. I fall in place, we fall in line. I'll never let you go. So when you hold my hand, do you wanna hold my heart? When you say you want me, is it all of me? Just one part. So when you hold my hand, do you wanna hold my heart? When you say you want me, is it all of me? Yeah. Mama said there'd be boys like you, tearing my heart in two, doing what you do best, taking me for a ride, telling me pretty little lies. But with you, I can't resist. Maybe Mama doesn't always know best. So when you hold me, am I the only one? Do you wanna know me? Or is this all just for fun? Mama said there'd be boys like you, tearing my heart in two, doing what you do best, taking me for a ride, telling me pretty little lies. But with you, I can't resist. No, no. Maybe Mama doesn't always know best. Mama said there'd be boys like you, too good to be true, doing what you do best, taking me for a ride, telling me pretty little lies. But for you, I'll take that risk.
I don't wanna play this game no more. I don't wanna play it. I don't wanna stay around here no more. I don't wanna stay here like rain on a Monday morning, like pain that just keeps on going on. Look at all the hate they keep on showing. I don't wanna see that. Look at all the stones they keep on throwing. I don't wanna feel that. Like a sun that will keep on burning. And I used to be so discerning. In my recovery, I'm a soldier at war. I have broken down walls. I designed my recovery. In the sound of the sea, in the oceans of me, I designed my recovery. singing. Tell me what they're saying. But I can hear the phone, it keeps on ringing. I don't wanna answer. I know that I used to listen. And I know I've become distant.
Good morning, guys. I think it's 7:59. So let's get started. Let me see. I think right now, how many people has been on? So maybe I'll slowly get started. I seen 10 people or 9 people already on. So yeah, we'll start as usual. So let's start at the friendly reminder. All right. Let me see. Now start from here. Um, so I think let's slowly get started. I think someone will get online and follow up. Good morning, Chris. How are you? All right. Okay. So let's get started with the friendly reminder. The first item that the due date is gonna be this Friday, April 24th by midnight. The assignment regarding your term paper, term presentation. Okay, I need at least 5 references. I already noticed that several of you guys has upload the 5 references. Okay, so which is good. So also I think the reason why I'm adding this assignment because I know that some of you guys already have a good start and get into your research. But then also for someone who may have a few challenge and also have some difficult in terms of time management, I think the 5 reference would force you to at least gather the information in a way that you can start do some reading, do some of your homework, so that you can craft up the presentation, which the due date is gonna be next Tuesday. So I expect that all presentation is gonna be in PowerPoint or the PDF form, which you're gonna be used. I think you will use your presentation during the PowerPoint during your presentation that I will schedule. Okay, I look at my material and I see that I still need a little more time. So the earliest that I will schedule you guys to do presentation, I will post the list of the order of presentation sometime next week. Okay, so get ready for the PowerPoint. Okay, presentation must be uploaded to Moodle website on next Tuesday. Okay, but then get ready, meaning that prepare, practice, and prepare your presentation in case that your turn, and anyone could have turn your first turn to do presentation on next Thursday, April 30th. Okay, so with these 2 homework, 2 activities, I decide to skip the quiz this week. Okay, I think I told you guys that I was considering looking into the activity thing that I assign you to work on. I want to be reasonable. Okay, so therefore I hope I think you are okay with no quiz this week. Okay. Also, I think you have another homework coming along, okay, which is the first programming assignment on dining philosopher, which you're gonna have to implement in P-thread. Last time, toward end of the class, I already talked about or give you some idea and sample of the code, how those things at least how to structure your logic, okay, in a way that you could solve this problem. So in fact, the dining philosopher will allow you to start learning how to write multi-threading, like parallel programming, that you can divide the work into multiple tasks. Even though dining philosopher, the problem is quite like the toy problem, but at least the logic allow you to start get some feel of how things work in parallel. Okay, also when you have multiple unit working in parallel, sometimes they may need some communication among them, okay? And then once they start do communication, specifically if they access or try to update the same share variable, okay? In that case, the synchronization must be ensured. You need to make sure that you control the way to access in a way that you will avoid the situation called racing condition, which that part of the code that could cause racing condition we call critical section. Normally, you have to have a mutual exclusion. I mean, particularly to pthread, you have pthread mutex lock and unlock, okay, before you enter critical section. But however, when you start using this synchronization or mutual exclusion, it could lead also to the deadlock, because sometimes if you lock something, but and then have either intentionally or unintentionally forgotten to unlock it, okay, then the logic gonna be blocked forever, okay. So in that case, you have to make sure that when using this mutual exclusion or mutex lock and unlock, make sure that you put the code in the right logic in a way that once some process lock it, then you have to unlock it, okay. So I think that an overall reminder that what's coming in terms of the deadline. I'd like you to pay a little attention to this, okay? So if some of you guys have any question, Ryan has question. How many slide would one need to come up with? I would say, Ryan, I post those requirements on the Moodle, but I mean, I think I mentioned that you could have 10 plus minus each slices, okay? Make sure that you have the good content, but also don't just like cut and paste and then make it like 50 pages, okay? So I think the good number would be 10 15 pages, and if you copy picture or diagram from somewhere, you need to quote the source where it come from, okay? Because I don't want, in my previous year we don't have Moodle, so I have my website which is public access. One of my previous students just cut and paste from some paper without quoting. In fact, the original author somehow probably do Google search, and he found out that his work has been copied, and he sent me a private message demanding me to take that thing off the website until it get code, and asked me to flunk that student, and then that student already graduate, okay. So I think you allowed to use or quote someone else's work, but make sure that in your presentation, put the original source to say this is this slide or this diagram, the original source from here, who is the author, and those kind of things, okay. So make sure that you acknowledge original inventor or the owner of that work. All right. Okay, so I hope I answer your question, Ryan. Good morning, Isaac. Okay, all right. So let's continue on chapter 7 or lecture 7 on deadlock. If you notice that so far from chapter 1 all the way to chapter 7, mostly we talk, or the content is centered around process or processes, okay. So I think this would be the last chapter before we move on to the next important resources, okay. Most processes or thread, I think it gravitate or center around CPU, because it's just like a unit that we need to manage, or your application unit or instance that is executing, okay. So I think that involves CPU scheduling, process management, and then we talk about synchronization, communication, and then now the deadlock, okay, which is the last lecture or chapter that touch upon the concept of process or process management. So you can see that in terms of operating system, we are heavily kind of lean toward processing, because in fact when you all use computer, Mostly you actually don't use directly the hardware. You use the software, that those software would run on the hardware, and then you have operating system underneath it to manage your application running here and there. And some of your application maybe have multiple instances, or you execute multiple for example, the system that consists of multiple subsystems that has a lot of processes that communicate to each other. And sometimes you may have application that you want to improve the speed, in which you may program in multi-threading. So therefore, you can see that whatever chapter that we touch upon, it covered the concept or idea of not necessarily that you're going to have to be a developer of writing a new operating system, but then when you start writing application, especially when you write a grand or complex application that you have a lot of subsystem or modules that working together, understand all these things is quite crucial. Understand all this concept of how the process get context switch, the system call get execute, the overhead of a certain aspect, the deadlock, the synchronization. They're all important in terms of putting a big picture in order to uh, come up or design a good complex system. Okay, as I think you all know that there are a lot of outsourcing, that programming kind of work maybe can be outsourced to somewhere. But I don't think that in terms of the designer, the people who responsible for overall system technical aspect, no one can take away from us. Okay, meaning that the job gonna be here if you understand all these fundamental things quite well. Without understand how all these nut and bolts working together, I don't think that you would be able to design a well-oiled machine or good complex system. Trust me. I Before I came back to academic teaching you past 20 years, I used to be a technical lead in the big corporation, one of the largest company in the world, AT&T. Okay, so I think with that role, I think it's around me to kind of see a lot of aspect. All right, so let's deep dive into Deadlock chapter 7 or lecture 7. Okay. I think this is an outline that we're gonna talk about the deadlock definition, deadlock problem, and then discuss or continue on describing the system model that represent this problem, so that we can characterize and then look into techniques how to handle the deadlock, which normally there are three aspects of those uh, uh, deadlock handling. Okay, which is deadlock prevention, deadlock avoidance, and then deadlock detection. Okay, so in general. Okay, oh, by the way, I think this is the main objective of this chapter, to develop a description of the deadlock, which prevent the setup process to complete that task by holding some resources that not letting go. Okay, in a way that it interlock kind of situation. Okay, and then we're gonna look into different methodology how to prevent or avoid the deadlock in the system. Okay, in general. Okay, this is not just for deadlock. General problem solving skill. Okay, I think this one you can start. You can apply to any problem that you want to solve in the future. Okay, so this is not in the book, but this is from my professional experience. Okay, both in industry as well as in academic. In fact, in the past 15 years ago, I was very active in terms of looking into a new method. Okay, so my group has been very productive. Okay, in terms of research in supercomputing, specifically in how to ensure or how to improve resiliency of large-scale supercomputer. So being productive, I think we have funding from National Science Foundation, NSA, and Department of Energy twice. Okay, so I think with that type of experience, together with industry, I kind of, trying to summarize a general problem solving skill that I think you can use in the future. And in fact, these are not rocket scientists, okay? I mean, maybe some of you guys may already know this. So I saw Carrick has asked a question: are we supposed to show code on the PowerPoint? Not necessary, Carrick. Okay, most PowerPoint presentation. I think you talk about the outline already put in the Moodle. Okay, uh, the main idea of the PowerPoint is to teach your colleagues, to teach the whole class on the subject that you are working on. If you are working on some sort of programming, yes, maybe you need to demonstrate and show the code, okay? But I believe that, from the topic that I have seen, no one working on the programming at all, because I asked most of you guys to work on doing research for your term paper presentation, something related to operating system, to runtime, to something that in whatever the concept of we have discussed in the class. Okay. So if you have more question, you can just type, or you can just do a Zoom meeting with me. We'll talk more. Okay. So coming back to general problem solving skill, these are an outline that I use professionally. Okay, first you must identify, okay, and understand your problem, because if you don't know your enemy, how would you fight and win against your enemy, right? So first you must be able to identify and understand what causes, especially the root cause of those problems. Okay, once you start understand and lay out what are the key stakeholder or key factor that cause those problems, okay, then you start perform some analysis. Okay, I mean, from what cause, to how. Okay, so after you do some analysis, maybe together doesn't I think if you have some question, ask me. Okay, if once you start understand, but by the way, bullet list 2 and 3, analysis and modeling and design, those could be a feedback loop, maybe go back and forth, because you may start do high level analysis. Okay, then after that you start create a representation of your problem we call models. Okay, and then you start do design, and then you may perhaps when you do design, you may do what if analysis design, meaning that if you come up with this design, what's gonna be the cost or the result? What would be the cost? Mean how expensive it is, how effective it is. Okay, so in that case, you may go in the circle a bit. Like we call iterative kind of approach. You do modeling, you do the design, and then maybe perhaps you go back and do analysis again. Okay, to see whether the solution would be the best possible or not. Because a lot of time when you come up with some solution, you may be restricted or confined by certain factor. For example, the cost. Okay, let's say that if your company has certain budget, okay, you cannot buy whatever luxury car in order to transport from people from here to there, because you have certain amount of money. So therefore, just transport some people, maybe perhaps you can use the truck or different other means. Okay, but in that case, you have to kind of consider other factor. For example, the reliability, the convenience, the quality of service, or whatnot. Okay, and once you having some good design, okay, then you start implement one of those, the best possible solution that you come up with. Okay, and then once you come up with the solution, okay, before you use it, you must test it. Okay, to validate whether your model, your implementation fit well with whatever your original intention or the model. Because initially during the design, you may predict that your solution, the model, will result in 20% improvement. Okay, but once you do implementation, you test it again to make sure that it follow whatever your prediction or whatever you decide or not. And then once everything tests and work well, then you deploy. Okay, so this has nothing to do with specifically to the deadlock situation, but this is just general problem solving that for me professionally, both as a professor that teaching here and then do research or high-end research a few years ago, including my industry experience, I used this methodology or overall methodology, okay, in order to solve the real world problem. Okay, so I hope it makes sense to you. All right, all right. So now let's deep dive into the deadlock problem. Okay, the deadlock problem is defined as when you have a set of blocked processes. Okay, each holding a resource and while waiting to acquire additional resource that held by another process. Okay, so you can imagine that you have to do something, but then you cannot complete the task except you have to complete two things. Okay, thing in the left hand side and the right hand side hand. Okay, but first you already grab the hammer. Okay, then you want to have the chisel in order to do your work, but then there's another guy holding the chisel. Okay, but then he's still working on it, so therefore you are blocked until you get hammer and chisel or the nail in order for you to start hammering the nail and then build the wall. Okay, so I think this is a situation that could lead to the deadlock. So for example, if your system has two tape drives, okay, and you have process P0 and P1, each of those process, okay, hold one tape drive and each need another one. Okay, so that mean, I mean, if you have two, it may form a circular web, meaning that the dependency from each other's, you are holding each other, so that you cannot proceed to make progress. Okay, now for example, maybe perhaps we can show you some sample code that last time I have shown you using semaphore in order to ensure the synchronization, because I mean in the case that when you using shared resources, you don't want two or more processes try to compete and then get to the shared resource all at the same time. Otherwise, it's gonna be chaotic. They're gonna be fight. They're gonna be some unpredictable kind of result. Okay, so therefore, some tool like synchronization tools such as semaphore can be implemented. For example, let's say that if you have two semaphore A and B, where you initialize both A and B to be one. Okay, then before this is critical section code. I think this is just a snippet of the code that I show you in the previous class, okay, regarding the deadlock. First, P0 trying to, execute operation called wait, which is you have wait and signal. There are two main operations for semaphore. Wait is an operation that you are declaring that you're going to enter critical section and then try to grab the key. If the key is available, then you enter it. And then in the case of semaphore, you use numeric value to represent the state in which you should wait and go. If the state of semaphore is greater than 0, okay, then you're gonna enter it. Okay, that means you're okay to enter and grab the key. Okay, and then you're gonna decrement that semaphore value by 1. So if you initially the initial value of semaphore A is 1, okay, then P0 try to execute wait A, then the P0 will enter it and then decrement A by 1. Okay, so therefore A now becomes 0. All right, then let's say that time T1, okay, P1 try execute wait B. Now the wait B B initially value as 1, okay, then P would allow to proceed, but then before it proceeds, it decrement B by 1. So now B is 0, okay? Now time T2, P0 try to execute wait B, B already 0, so therefore P0 get blocked here. And then time T3, P1 try to execute wait A is already being value as 0. So then P1 gonna be blocked here. So therefore, both gonna be interlocked, okay? Both gonna be blocked forever, except until maybe perhaps you have another process to unlock all this, okay? So in that case, I think either you have to rewrite the code in a way that you don't have, it would not lead to the deadlock situation. So I think this is a general idea how the deadlock could occur. Okay, here is another picture that in a normal real life situation. By the way, I have not seen in US that you have two-way street. Okay, coming, I mean like both sides, and then somehow when you cross the bridge, okay, then it become one direction or one-way street. I've seen a few places in other country in the world, because I think, as you know, I travel quite a bit around the world. A few places in Costa Rica or Ecuador, I've seen this, and I have no idea. The local people know how to give way to other people. I don't know whether, I mean, the even though they come almost at the same time, but they know the ways that they let other people go. I think if you have this type of uh, traffic in this country, I think we're gonna be in big trouble. Okay, uh, so but anyhow, consider that, I mean, if the traffic is only one direction, I mean at the bridge, so you have bottleneck here. Each section of the bridge can be viewed as the resource. Okay, let's assuming that this is the common resource that all these process want to share. So I mean, if the deadlock occur, it can be resolved by one car is backing up. Okay, so I think this is the same idea as in the computer system. Maybe if we run into a situation that we have this bridge, okay, or bottleneck bridge, okay, that only allow one car at a time to pass through. Okay, so in this case, somehow if we don't arrange in a good way, okay, uh, you may get deadlock because of here, if you have all block, and then if this car approach, I mean, to the bridge, and if this car can't back up, so therefore you may end up lead to the starvation, okay, or the deadlock may happen. Okay, so with this type of situation, how do we solve it? So in that case, we need to somehow represent this and find way, perhaps maybe we have some buffer zone here, so that one car can back up here and then the other car can go. Okay, or maybe we have some traffic lights. Okay, so that we can regulate, I mean, the pass through on both sides. Okay, so I think this is some idea that, as I told you, look into the problem and see what caused the problem, and then maybe perhaps come up with the solution. I mean, sometimes someone say that, why don't we just put the traffic light there? But as I told you that sometimes middle of nowhere, you don't have even electricity, you don't have even signal of your mobile phone there in middle of nowhere. So in that case, maybe perhaps the way they decide this, because this may be a deep canyon down there. And someone may say that, why don't they just build like two-way bridge with the whatever the location? It may not be possible to build two-way bridge. So in that case, before entering that section, maybe they can come up with buffer zone or something, so that there will be some solution would not or alleviate the deadlock situation. Okay, so I think this is just some general idea, but I think later on we're gonna look into how do we define a system model that we can do some analysis, because this is just one resource. What if you have multiple resources? Imagine that in your computer you may have resources such as CPU. In fact, CPU, how many CPU you have? even though you said I have one, but then one you may have 8 cores, you may have 12 cores there. So that means one CPU you have 12 units there, right? And then beside that, you have CPU, you have memory, you have graphic card, you have various devices, and then the devices that not only use plug into your USB, but then you have all Bluetooth, all these different type of connectivity like display port, USB-C, Thunderbolt type of device. So with a modern computer, you have multiple resources. So now, in order to ensure that we be able to detect the deadlock situation so that we can solve it, then we have to come up with system representation we call system model that we'll talk little later. But first, let us define what caused the deadlock. Okay. I think this is what I mentioned to you a little briefly. So this is the system model that you could represent a given problem specifically to this computer system. For example, you can define resource type as R1 to RM, R1, R2, etc. to RM. Okay, that you have M type of resources. Okay, each resource could, for example, R1 could be CPU cycle, R2 could be memory space, R3 could be different thing up until RM, okay? And then each of the resource type Ri, okay, it has Wi instances. That means, let's say that you have CPU. You may have system that has 2 CPU. Each CPU you may have multiple cores there. So in that case, Wi define the instant or number of copies of that resource that you have. Okay, and then now with these resources, okay, which mean the supply. What about your demand? Demand is coming from application of processes, right? So here we define process as P1 all the way to Pn, okay? That define process number 1, process number 2, all the way to n number of processes, okay? And then each process in our model that we will study in order to detect the deadlock, there are 3 type of operation, okay, high level operation. First is making the request of that given resource or that instance of that given resource, okay. And then the second operation, one is request. If it grant, then it's using it, okay. And then after it finished, then it released, okay. So these are the model representation that we could come up to represent the problem in order to detect the deadlock. You guys with me so far? I hope, I think just follow or visualize this. As I told you, even in many of my previous classes, operating system sometimes it could be very boring class. You know why? Because a lot of those are conceptual. You have to visualize how those things work together. In fact, you are giving the box, okay, which means the box that you're giving, the computer that you're being given, there are a lot of things inside there, okay. But then for us who are the creator, not the user, again, all you guys study here, okay, deep dive into computer science, you be the creator, not the user. As the user, you don't need to know very detailed this, but as the creator, it's important for you to understand how things work together, okay. But anyhow, let's move on. Now let's describe the characterization or characteristic of deadlock, okay. Deadlock would occur, okay, if these four following condition hold simultaneously, okay. This is important, guys. You have to know this, okay, in order to know that well, if the deadlock will happen, these 4 conditions will occur simultaneously, okay. First situation, if you have a situation that it requires mutual exclusion, that means if you have 2 or more processes, okay, that working together, and then you have only one, you have 2 that trying to access the same share resources or share variable, okay? And then as you know that if we don't impose or use synchronization or mutual exclusion, then the result would be unpredictable, okay? But then as we know that when we try to enter that section of code, okay, that will access the share variable, we call critical section, okay? Then when we have to put the mutual exclusion like lock and unlock, okay? So in that case, the mutual exclusion lead to the situation that only one process at a time can use the resource, okay? So that is one condition out of these four that would lead to the deadlock. All right, guys. So I think you with me. Then the second situation or condition that must hold simultaneously is hold and wait. Okay. So if you have a process is holding at least one resource and is waiting to acquire additional resources, okay, that held by another process or other processes, okay. So not only mutual exclusion, okay, which means that process is only one process enter and then using the resources, okay. Then at the same time, okay, that process is hold that resource but also waiting to acquire additional resource, okay, that hold by the others, okay. You got with me? Then the third condition is no preemption, assuming that your situation, your system would not allow preemptive or preemption activities, okay. That means a resource can be released only voluntarily by the process that holding it, okay, after the process has completed its task, okay. You cannot just operating system are not allowed to just take away the resource, okay. So I'm saying that if you have the situation that the preemption is not allowed, okay. So three conditions: mutual exclusion, hold and wait, okay, and then no preemption. But these three, when they occur simultaneously, it may not lead to the deadlock, okay. The last but not least situation that when all these things happen and then create a circular wait fashion, okay, which define as there exists a set P0 to P1 all the way to Pn and then back to P0 again, okay, of waiting process C, such that P0 is waiting for the resource, a resource that is held by P1, and P1 is waiting for the resource that held by P2, etc., until Pn minus 1 is waiting for the resource that held by Pn, and then Pn is waiting for the resource that held by P0, okay. So these four conditions, okay, when they occur simultaneously, possibly it could lead to the deadlock. So therefore, in order to eliminate or to avoid to solve deadlock issue, if then we have to be able to break some of these conditions, okay, or maybe prevent if this is gonna happen, do something else, okay, in order to avoid these four conditions that may happen altogether. Make sense? So I think you have to remember here. Deadlock characterization, it happens when these four conditions hold simultaneously. Mutual exclusion, hold and wait, no preemption, and circular wait. Okay, I just emphasize so many times because I think this is important. All right, guys, let's move on. So now, once we know that these four conditions, okay, now coming back to the system model that we talked about early on, remember we talked about we have set of P, which is process, and number of processes, okay, and then we have the set of resources R1 to Rm, in which each R or each resource we have number of instance W, okay. And in that case, we can draw we call resource allocation graph, which is the graph that represent how the process request make use of those resources and release them. Okay, and then then we would define two type of vertices. Okay, um, and then we have edge that connect to those vertices. The set of vertices consists of the first category is set of processes P, which is P1 to Pn. Okay, and then we have set of vertices R, which is represent the resource type or resource in the system, Ri to Rm. Then we have two type of edges. Okay, you have to notice that the direction of the resource. Okay, so if we have P pointing to R, Pi pointing to Rj, that means that is request edge. P process Pi is requesting for the resource Rj. Okay, and then we have the directed edge from R to P. That means we have assigned that given resource Rj to the Pi here. Okay, so you have to make distinction between two edges. Okay, one is request edge, another one is called assignment edge. You guys with me so far? Now I think we're ready to give example or draw this resource allocation graph representation. Okay, so now Isaac has asked, can we set up a one-to-one? Yes, Isaac, you can use the link that I post last week. I will copy that link again on Moodle to whatever the current week. Okay, I think we can use the same Zoom resource. Okay, and send me email what time you want to speak with me, because I don't want to just go nowhere and just stick and put on the laptop on my lap and wait for 2 hours and cannot move. Okay, I think I would love to talk to any of you guys, but send an email that between 1:30 to 3:30. Okay. Oh, by the way, tomorrow I'm running a data science initiative that I'm pushing to create our new program or concentration called data science. Okay, from 1 to 3 o'clock. So anytime, otherwise we can speak anytime. It could be morning, could be after 3. Send me email, give me the lead time a few hours, and then we can get on the Zoom together. Yes. Okay. All right. So let's move on this resource allocation graph. If you guys notice that once a while I look to my left because I have my iPad here, that I'm noticed. Your question here. The my whatever main computer here, it covered the whole thing with my slide. So in that case, I can't see the answer. So once a while I may be a little delay answer your question, but please feel free to type anything there if you have question. Now let's look into before we start drawing example of this resource allocation graph. Okay, now let's deep dive into the representation of processes or set of processes and set of resources. Okay, so we have this circle that represent a process. Okay, and then we have this square that represent resource type. And if you notice that we have tiny square here, this little square here is represent instances. Okay, so in this case we have 4 tiny square within bigger square, which is within this resource type. This given resource has 4 instances. All right, guys. So now, as I told you, we have the request edge, and then we also have assignment edge. Okay, so in this case we have Pi is pointing to Rj. So process Pi is requesting to obtain the resource of Rj. Okay, one instant or whatever, how many you want to declare. Okay, so if you have more than one request, then one instant, then you should have more edge there. Now in the case that remember we have another type of edge we call assignment. Okay, so if we have the arrow direction, okay, to what process, a process, that means RJ has been assigned to PI already. uh, and another word is PI is holding an instance of RJ. Okay, so I think these are a vertices, okay, or the node representation that we're gonna draw resource allocation graph. And you can probably can guess that if we start drawing this resource allocation graph, and then we start seeing that it starts forming circular wave. You guys remember four conditions, okay? Mutual exclusion, hold and wait, okay? No preemption and circular wave, okay? So now I think as I introduce you the resource allocation that graph that represent by vertices and edges, okay? And now vertices could be processes or resources, and then you have edge, okay, that one is holding, another one is requesting, okay. Then you can start guessing that, okay, if we draw how this application set up application attempt to use the resources, and we can predetermine, okay. And then if we can detect the circular wave, okay, so in that case if the circular wave gonna happen, then we can just reject, okay, or somehow do something so that we can prevent that circular wave, and therefore we will be able to avoid the deadlock. But what if you say that you have n number of processes, which one you're gonna choose? Maybe perhaps when I say which one you're gonna choose, not giving the resource, okay, because you said that there is no preemption, right? So in that case, I mean, among all those processes, you can see the priority of the process. Maybe choose the one has low priority, and then not giving whatever the resource to that one, so that we can break the circular wave in order to prevent the deadlock. Okay, but then someone may question, maybe that process may lead to starvation. Well, then you can start apply aging too. So I mean, previously this process may have low priority, and then when let's say that one turn that this guy has to wait, then you can start improving the priority. Okay, so I hope you start seeing some picture. But I think we'll look into, and then I'll show you. I think I'm just trying to kind of entice you or inspire you to start visualize what coming next. Okay, once you start figure out this, okay, that means you already have some good foundation of whatever the knowledge. Okay, when people start talking something, then you can start visualize, you know, what's gonna happen and how you're gonna come up with some solution. Okay, that's the way, I mean, I see a lot of time myself when I make this discussion or brainstorm to come up with new innovation or new solution among the war room. You know, a lot of time, especially I miss my industry. Okay, a lot of time we get a new problem, and then we call everyone into the, we call meeting room or war room. Okay, and then we start brainstorm and discuss, I mean, some problem. But before we get into, you know, brainstorm, then someone got to define problem statement so that we are on the same page before we start giving some idea. Okay, let's start take a look at the example of this resource allocation graph, guy. Whenever I grab the cup of tea, that means I think it's probably close to the midpoint, and then my throat start getting dry. Sorry, guys. So take a look at this graph. Okay, here this situation, it's representing a situation where you have three processes running, P1, P2, and P3. And then in this situation, you have four type of resources. Okay, resource R1, resource R2, resource R3. Okay, by the way, I think they misdraw this, or they casually draw this. This should be rectangle. Okay, then R1 has one instance of resource one, and then R2 has two instances, R3 has one instance, and R4 has three instances. Okay, here we have P1 is requesting to get resource R1. Okay, and then P1 is holding R2. Notice by the arrow here, guys. Okay. Now, meanwhile, P2 is holding R1. Okay. And then P2 also holding or using R2 as well. And then at the same time, P2 is requesting for R3. And then P3 is holding R3. If you take a look at this graph, okay, do you think it's going to cause the deadlock? Guys, notice on the arrow, would it go in the same direction? It's not, okay, because this one go this way, and then you have this one go this way. So it does not create a circular wave, okay? So therefore, this one would not lead to the deadlock. Why? Because of, for example, now let's say that P3 is using R3, and then when P3 finish it, okay, then we'll release R3 back, right? Okay, and then R2 is using P2 using R2. Okay, that's good. Carrick, I think there's no deadlock. Carrick, just type in the chat room, answer that there's no deadlock because of there's no circular weight here. And then, you know, I mean, so R3 is already available because P3 already released. Now P2 is using R2, and then R1, and then P2 is finished, release it back. Now P1 can use both. So there's no deadlock, okay? Because of, again, easiest way, the arrow does not go in the same direction, okay? By the way, let's say that in this case, let's say that instead of this arrow, if this is this arrow, okay, going to this direction, would it cause the deadlock? I give you 1 minute. Well, Isaac said no. Okay, I don't know whether he meant this one or not. But anyhow, in this situation, even though it looked like the circular weight, but then if you notice that you have 2 instance of R2, that means, I mean, this one can split into 2. In fact, you can think about it split in or it clone itself into 2 nodes, okay? So therefore, it still would not form the deadlock, okay? Except if you have 1 instance and the arrow go this direction, then it could cause the deadlock. But does it make sense? Let's take a look at another example, okay? Yes, good job, Carrick. Now, if this situation, would this lead to the deadlock or not? You can think about this, could be break into 2. So P1 would have R2's prime here, right? And then here, this circle is not a circle anymore, okay? However, you see this circle? Okay, so this one is deadlock. I think you guys start seeing the how to solve the deadlock problem, okay? Which means if in the case that when before you run any program, okay, and then if you could create this resource allocation graph, okay, and then determine maybe part of your job scheduling and also at an IO assignment, okay, and then once you start create this resource allocation and then start detect the safe zone or not safe zone. When we say safe, that means there's no circular weight, but then it's unsafe. If you detect there's some circular weight there, okay, then that may lead to the deadlock situation. But by the way, all those 3 other conditions must be held, okay, simultaneously. Does it make sense, guys? Yeah. Could you explain the last one more time? Yes, Ronco. Yes, Carrick. Because if you look to the left circle here, the left circle here, since R2 has 2 instances here, okay, that means this could be break up into 2 boxes here, right, with 1 instance. So therefore, on the left hand side, there's no circular weight, Okay, but then if you look into this the right hand side subgraph, okay, then you even though you break this one into separate, okay, then when you see the arrow here, okay, that means P2 is waiting for R2, or P2 is holding R2. Meanwhile P2 is requesting for R3, and then R3 is holding by P3, and then P3 is requesting for R2. So it forms circular wave here. The arrow going to the same direction. You notice that the arrow going to the same direction, okay? And then you don't have any extra instant. So therefore, it lead to circular wave and eventually possibly could create the deadlock. Make sense, guy? Oh, previous slide, okay. You mean this one? Sure. Okay, let me do this again, guys. You can take a few minute break. Okay, let me just explain to Ronco. In this case, there's no circular wave, okay, because two things. One is arrow does not go to the same direction. You can see this arrow, this go to the same, but then this go opposite, okay? And second factor that would not cause the deadlock because there are two instance of R2. So in this case, it could break this one into two little square, okay? Therefore, it break up the chain, okay? Make sense? Yes, okay. All right, guys, so I think right now is 8:55. Let's take 5 minute break, okay? And then meanwhile, if someone have some question, type, you can type, okay? I will resume, go quickly to my bathroom, and then have another sip of tea, and then we'll resume around 8 o'clock. Oh, no, 9 o'clock, okay? Because we already passed 8. And then once we finish chapter 7, then you guys want me to repeat on the dining philosopher programming homework, you want more information, I don't mind to go through. I don't mind to, in fact, upload some sample code because I already prepared one sample code for you. And then I can explain a little more detail. So I'm hoping you guys start looking into the dining philosopher, okay? So I think we'll come back in 5 minutes.
things of God, compassion for the lost, the widowed and the orphan one. To love like you love, we are seeking after you. We long for something more. Your spirit leads us on into the things of God. Your passion's our command as we run by your hand into the things of God. Faith, truth, and hope, forgiveness to let go for the things of God, the broken and the weak, for those we often fail to see.
All right, guys. Me back here. Yeah, while I was teaching you, my Wi-Fi camera in the ducks box kind of alert me that there's some movement in my wood ducks boxes or nesting box that I built. Two of them, and then I just quickly download, and you can see that the mama ducks just got into the box, and I think she's trying to lay the eggs. I think this year's quite late because of I've been busy traveling before this COVID, so I didn't go out and clean up in the areas. Otherwise, we should have the first hatch. I mean, last year I think the first jump is around end of March, and I think this year it's quite late, so we have only one eggs in the box, as you see here. Okay, so I think this is some other activities that I do beyond um, teaching. I think I enjoy create my backyard project and do some photography. Also help conservation. I think every year we produce 40 to 50 ducklings. Back to the wild. We have maybe 10, 15 boxes. I just fortunate to live at the lake. So step 10 step away from my house. I build the duck blind. I'm not shooting the duck, but just watching them, observe their behavior. Okay. All right. So let's continue on our discussion on the deadlock. And I think I will go to maybe show you some more sample code and run the program for you. Okay. I think last time I just have PowerPoint on the dining philosopher lecture or suggestion. But I think we'll give you a little more head start, at least, because we are not have face-to-face meeting. So a lot of time, allow me to maybe I don't call spoon feed, but I think provide you a lot of help. In fact, I mean, I also want you to kind of discover some of those stuff by yourself, because I mean, easy come and easy go. Okay, if you figure it out by yourself, a lot of time you remember it forever. Okay, so but anyway, let me just continue on, and then once we finish chapter 7, which is short chapter, then we'll show you more on that code and run the code. Okay, so I think we already talked about this. Okay, what about this? This is another example. Okay, it's gonna be the same thing. You can do some analysis. Okay, I believe this one would cause there's no deadlock because of it break up. I mean, so you have multiple of those instances, and then one instance is being used after it's already finished. Then you have that square could be broken up into two, okay? Because you can imagine that anytime when you have more than one instances like here, okay, that could virtually, you can think of like two resources that each resource has one instance, okay. So in this case, the reason why there's no deadlock, but even though it look like more deadlock here, because you don't have another circular weight here where you have two circular weight kind of interlock to each other. But in this case, P2 is using R1, and then when P2 finish, then P2 just release it, okay, and then make this R1 to be two instances, and then the two instances of this one, it does not, the reason why it does not form the deadlock here or the circular weight, because this one can be broken, so that your chain, your circular chain is got kind of separate by these two instances, okay. Does it make sense? All right, okay. So now let me summarize the idea, the concept, okay? The concept or the idea in order to deal with the deadlock is one of the technique is to use these tools we call system model or resource allocation graph, okay? Which in this case, you have to predetermine how application, I mean, using or your process using how many resources, what type of resources, okay? So all this has to be declared in order for you to start building up this resource allocation graph. For some random situation that you don't have predetermined resource uses, okay? In that case, maybe we can find other technique, other solution we call deadlock detection and recovery, okay. And some situation maybe perhaps they assuming that deadlock would not happen. If it happened, then the recovery would taking care of those things, okay. For example, in my past experience, okay, when we develop this telecom system, where telecom system may consist of 10, 20 processes that they're working together, okay. Some process may perform digit analysis, okay. When I say digit analysis, when you type, have you guys thought about, when you type the phone number like 13825375557 or something like that, this number when you type, okay, this information will going into we call central office, okay, and then it will figure it out. If you type, we call NPA, that means the area code, okay. You can strip off one because which is one is international code, okay. Let's consider like 318. 318 is the area code. So in that case, this number is used to route to which of the central office that this phone needs to be terminated, okay. This is just like a network routing, okay. I mean, when you start seeing that IP address, you see 138 dot something dot something, all those I mean, those number, category of number represent something. The same thing as when you start typing some telephone number, it will determine which area code, okay. Then it will send to the central trunk of the whole area, and then NPA, which is the area code, and then the next three digits like 253 or maybe 257, okay. That indicate which office or meaning central office it should route to, and then you have last four digit, which is your phone number, which the whole thing is as your phone number, okay. Does it make sense? So I think what I'm trying to say is that in telecom you have this digit analysis, telephone number management, and then you have the routing kind of modules. You have a call forwarding module. You have a lot of module work all working together, okay? And some of those modules, okay, we in fact during the testing we know that that application, that process requires certain type of resources, okay? So therefore we could predetermine, okay, and then make sure that it would not lead to the deadlock. So in that case, we can do some analysis and start drawing this resource allocation graph, okay? But in certain situation where you don't have this predetermined the resource usage, and then plus your system require a very high performance, very short time, very time critical type of thing. Because imagine that if you have to dynamically build the resource allocation graph every time, those overhead would add up to the performance. It slow things down, okay? So, but all and all this thing can engineer. If you think that, your system the deadlock is very critical. You're not allowed to have some deadlock, because if deadlock happen, you cannot recover, or the recovery would cost more. So therefore, you can pre-engineer, enough resource. You can test or before you deploy to understand what type of resource that require, and then build you can use resource allocation graph to build and then determine whether there's some circular or not, okay? If there's no circle, then there's no deadlock, okay? However, in case that if the graph contains some circle, if only one instance per resource type, then it would cause to the deadlock. But then in case that you have several instances of the same resource type, it's possible cause the deadlock. It depends on the usage. If the usage is many more, the request many more than the supply, okay, in that case the possibility of the deadlock it increased substantially. Some of these you can determine by statistic model as well, queuing model or whatnot, if you want to get into more theory, more complex, but in fact, in the real serious system, a lot of during the design and analysis, they do all this, because everything costs. If you add more hardware, you add more code to handle those things, okay? Everything costs to the solution. All right, so let's recap this, okay? So I think the main theme, the main idea of the deadlock, you have to know these four conditions: mutual exclusion, hold and wait, no preemption, and circular wait, okay? These four conditions, when it happens simultaneously, it could lead to the deadlock, okay? So therefore, if you could avoid, if three of these you can change, okay? But the circular wait is based on operating system can allocate the resource or not granting it, or schedule the task to do certain things, okay? In that case, you can break the circular wait by using certain scheduling mechanism or resource management mechanism in order to avoid this circular wait, okay? As I mentioned, okay, the method for handling deadlock is to ensure that you will never enter the deadlock state, okay? And then allow the, or in some situation, you allow the system to enter the deadlock and then recover it, okay? So in Unix or Linux, okay, is ignore the deadlock problem, assuming that it never occurs, okay? But then when it happens, okay, then the system admin, either you can use the system admin or manual intervention, or you can develop a tool in order to solve the deadlock problem. In fact, simply way to solve, or to once you detect the deadlock and then you want to solve it, you just restart the process. Because when you restart the process, the pattern how those processes using the resource may not be at the same time or the right time, okay? One way to detect whether the system caused the deadlock without going in or create this circular wait or not. Let's say that if you have a process that handling call routing, okay, and this one is very important, meaning that it has to work all the time. Okay, so in my past experience, any critical process, then we will create a mechanism called heartbeat. Okay, heartbeat, like heart, HEART, heartbeat mechanism. That means we're gonna watch for that particular process or application. Okay, and that application should send a heartbeat, just like human. If you guys have no heartbeat, that means you're dead, right? The same thing as the process. Okay, if any process that's important, then we'll dictate, we decide, okay, by decide that that process at least every certain minute, maybe we can have those as tunable. Let's say that every 5 minutes it should send one heartbeat. A heartbeat just like one network package. If you guys have used a command called ping, P-I-N-G, okay. If not, then you can Google this command ping. Ping is a command that you can send small little package to the network, and then the network, that node will ping back to you to say that I'm alive. Okay, so in that case, the cheap way to check whether my application is locked or do nothing, because the deadlock, what the deadlock costs, would cause your process to hang forever, right? And then if that process is your critical process, then you can implement the heartbeat mechanism to that process. Okay, so therefore, if you don't see the heartbeat come back with interval time that you engineer, then you can assume that maybe perhaps the deadlock happened. What do? Then you would have a recovery process by first kill process A, process B, process C in order to recover something, or maybe reboot the whole system. Okay, so that is some attitude or some aspect of how this deadlock being handled. Okay, sometimes you may want to predetermine by detect the state. Sometimes you may just let it go, let it happen, and then recover it. Okay, make sense? All right, okay. So I think in summary, okay, in there are three methodology that being um, kind of study, okay, in order to handle the deadlock. The first one we call deadlock prevention, okay, which mean in the short kind of definition of deadlock prevention, make sure that those four conditions would not happen or won't happen. Remember that four conditions? I'm not going to repeat anymore. I repeat so many times. Second one we call deadlock avoidance. Okay, that means the process declare what they need beforehand, and then you can start determine, circular weight or not, and then if it's gonna cause circular weight, then you avoid it. Okay, and then the last but not least, as I told you, in fact, in the real world, it used the last approach. Why? Except if your system is so mission critical, okay, then that means no single failure, no single deadlock. Okay, then in that case, you have to assure or make sure that you implement deadlock prevention or deadlock avoidance. Okay, for deadlock detection is let them fry, let it happen, detect later on, and then recover it. Okay, why is so? Because it's so cheap, it's less complex to avoid, to prevent. You have sometimes when you have system that has maybe 100 of component that can be used, you have 100 processes that can run simultaneously. Imagine that if you have to create a resource allocation graph that you have to have a set of 100 processes or more. You have a set of 100 of resources. Okay, your graph gonna be very busy. Okay, so therefore the first and second method, overhead can be overwhelmed. Okay, therefore the last method, okay, may be the most appropriate. Make sense? All right, so let's move on. Maybe talk a little bit, as I told you, these four conditions that we already discussed on deadlock prevention: mutual exclusion, hold and wait, no preemption, and circular weight. Okay, so in this case, when you gonna try to ensure that there's no deadlock, you want to prevent deadlock. Okay, restrict the way that the request can be made without causing all these four conditions. Okay, Then now the next one is deadlock avoidance. Okay, it requires system to declare what are resources that to be used. Okay, uh, ahead of time. Okay, this technique is simple. Maybe most useful model if it's possible, because sometimes it's not possible because some application is more dynamic. Sometimes based on certain situation, certain resource may being used, so you cannot predetermine. Anytime that you can predetermine, there's some certain situation that you can predetermine the type of resources and how many resources you want you can use and what time. Okay, so and if you know all this, then in this case you could create resource allocation graph. Okay, so that you can run deadlock avoidance algorithm in order to determine whether it's safe state or unsafe state. Okay, so if resource allocation graph is safe state, that means it would not lead into the circular weight. But then you have also to consider if your resource has multiple instances. Okay, uh, it may or may not cause the deadlock. It based on the way that resource get used. Okay, if you have a few number of resources but you have high demand of processes that want to access those resources. Okay, in that case is the uh, probability of the deadlock uh, increase significantly when you have high demand and then fewer resources. Okay, so in a way that the deadlock avoidance is I think some predetermined kind of information, and then you're running the resource allocation graph in order to determine whether it's safe or unsafe state. Okay, and then last but not least, as I mentioned, okay, I already talked about in general idea, allow system to enter the deadlock state, detection algorithm and recovery. And the easiest way to detect algorithm or tool is heartbeat mechanism. Okay, as I told you. So I think this is a safe state and unsafe state. Okay, this is algorithm to determine, and it, essentially the way to detect the safe state is detecting whether it's from the circular wave or not. So this is a lot of verbiage. Okay, but the main idea is easy. Okay, as long as you know, I mean, when you create the resource allocation graph, if you determine whether it's from circular wave, if it's not from circular wave, okay, then it's safe state. Otherwise, if it forms circular waves, okay, then it becomes unsafe state, which is I will go back to that slide, but this is what it show you. Okay, you have safe state and unsafe state. Okay, where unsafe state, it may not necessarily create deadlock. Certain subset or probability of unsafe state would lead to the deadlock too. But then once you start entering, you know, unsafe state, then you have to watch out because it could cause the deadlock. If you are in unsafe, you are in safe state, then you don't have to care anything. You can just let go, because if you start doing something fiddle around, anything that you do unnecessary, okay, then it will add up to your performance kind of, you know, I mean, bottleneck. Okay, so in that case, do thing is only necessary. Okay, now so I think this is the summary of a way to handle the deadlock. Okay, if the state is system state is safe, then there's no deadlock. If the system is unsafe state, possibly the deadlock could happen. Okay, and then to avoid it, to ensure that the system never enter an unsafe state, that is the deadlock avoidance. Okay, makes sense. I think we pretty much killed the deadlock, and I hope you understand. And I think this is just more descriptive or the description how the resource allocation graph work. In fact, we already talked about, you know, the pictorial representation, which I think is probably clearer. Okay, so you can read this. Okay, but I think the concept, the idea is just like the same thing that I show you how this graph is being drawn. Okay, all right. This is unsafe state. Okay, well this is this is safe state, because as you see that the arrow does not go to the same direction. It come here, but then it go against, okay? But then this is unsafe state, because here it going to the same direction. Make sense? You see this arrow, this arrow follow the same direction, okay? I think I will stop at this point for the lecture, or this deadlock situation lecture. Okay, what I would do next is I'll talk more on the homework. Okay, the dining philosopher. I hope it's okay. Okay, I don't try to repeat it, but I just want to. Last time I didn't show you um, how to run the program. Okay, so now let me go back and then go to dining philosophers again. Where's my project 2? Okay, so I think we already talked about this. I'm not gonna repeat this one. I already upload this. Okay, so I would show you this program. Okay, so let me show you this program. To start with, let's say that before you start running this program, download my pthread sample code. Okay, the pthread sample code, I would say that the third one. Okay, let me go to pthread with S. Okay, vip33.c. I would say that pt3.c would be the closest or the most useful if you want to get started. Okay, and then you can take a look at my PowerPoint, what I added there. Okay, so let me just show you pt3.c again. Okay, as you see that pt3.c is a simple sample code of pthread. Okay, where we create a number of thread there. Okay, and as you know that let me go back here, the requirement here. Okay, the problem that I'm asking you to do is simulate dining philosopher problem. Okay, and but then the number of philosophers. Okay, I'm required that do not fix to number 5. Okay, so in that case, the dining philosopher, the number of dining philosopher can be specified by let me just get larger screen. Okay, specified by the second argument. Okay, from command line here. So this is number of dining philosopher D field here. The field PHIL. Okay, so the second argument, this is number of each. Okay, so now coming back to this program. Okay, P3 4.c. So the number of thread is just like number of philosophers there. In this case, I think my suggestion, maybe you can start with this version and then make sure that you understand the code. Okay, and then this code, what it does, okay, it will create a number of thread by putting in this loop. Okay, so for I equal to 0, I less than n threads, and then I plus plus. Okay, so in this case, it will loop this n thread times. Okay, so if we specify 20, okay, if we specify 10, it's gonna go 10 times. Okay, however, when you start doing the homework, that dining philosophers, okay, you don't need this one, but you can define number of thread as integer. Okay, but then take the second argument. Okay, and then assign to variable n thread here. You got with me? So that means whatever this second argument, okay, take that one, I mean from mechanism called argc and argv. As I told you, you know, the main logic is read the command line input as a string, and then use argc and argv, where argc define number of arguments from command line that including the name of your program. Okay, so in case that for your dining philosophers, okay, you would have three arguments. Okay, first argument is the program name, second argument number of each, okay, and then the third argument is uh, the dining philosophers. Okay, and then after you get argv, okay, then you use a to I, okay, in order to convert. Okay, so now let me just I'm jumping back and forth. Okay, so let me start explain pt3 again quickly. In this pt3s, okay, you create number of threads, but here you hard code by define here. In your homework, I think instead of you hard code 10 here, you can predetermine, okay, pre-create number of thread as 32. Okay, and then the actual termination condition using the value from the argument that you take from the command line. Okay, so in this case it will create this number of thread, but then the normal logic for the master thread, once you create number of thread there, okay, then you would wait until all that children thread complete by calling pthread underscore join with whatever the handle thread id handle there. Okay, and in this example, the function called thread function is a function in which, you know, for you to implement dining philosopher is a philosopher logic that will think and eat. And while think and eat, he will try to grab the left and right chopstick. Are you guys with me? And then in order to solve the problem of the deadlock or potential deadlock, then you apply a symmetric solution. Okay, because if you just do a simple way by every thread or philosopher do all at the same do all the same thing by grab the right first, okay, then in that case potentially all philosophers have the right the chopstick on their right hand, but then the left hand when he tried to grab, because of the neighboring guys already grabbed, you know, the right one, and then therefore the left one would not available, so therefore you're gonna run into the deadlock situation. So in this case, my suggestion for you to implement this by determine the index. So you have to pass the index to the thread function, okay, and determine whether that index is odd or even number. If the odd numbers, okay, here is the logic. If the odd number, okay, make the odd number to first pick the left chopstick and then the right one, and then the even number pick first the right one, opposite one, and then pick the left one. So in this case we call asymmetric solution. Okay, now coming back to this one, okay, here pt3.c, all it does just do count plus plus. So in this case you have to replace this, okay, by try to grab left and right chopstick based on odd and evens, okay, and then also you know you have to track the number of each too, because as I mentioned to you that the requirement, the first argument after the name of the program would be number of each. If I say 5 times there, this is not going to be global count, it's going to be count particularly to each dining philosopher. So in that case you should have a local variable called count, okay, which initialize to be 0, and then you're gonna compare to the total number of count, okay, which is global, to see whether it reached there or not. So in this case you may want to put you may want to add a while loop like while one, and then have the condition when, you know, your eating number of eating reach the count, the global count, okay, then you would exit and then terminate that function, okay, or that thread, okay. So then you go back to the main thread. I already run this program for you, okay. Also I just happen to modify this version. I'm gonna upload this version if you guys want to. Which one? I thought I did. Let me see. PWD. No, I have to be in here. VI. Okay. All right, guys. So this is the version that I'm gonna give it to you. Okay. And then let me explain this to you a little more. Um, this is would be something that you can start with. Okay. This is similar to what I have put or capture the screen and then explain to you in the class. It looks similar to what I just showed you in P33.c. So I would encourage you, first play with PT3.c, change some parameter there like number of thread there, compile, run the program, get comfortable with, okay? And then maybe perhaps look into this program. Or if you want you don't want, easy way, I could hold off this and then maybe give you by next Tuesday if someone make the request, okay? I don't want it to be too easy class and then you're not motivated to learn more, okay? I think you can tell me if you want. I don't mind to just post this one, but otherwise I'll hold off, but then I'll show you. And I'll walk you through. So then you can go and update or modify from pt4.c, okay? So let me just walk you through this sample code, okay? Which I think if some of you guys would like me to share this one, you can give me on this live chat, okay? Otherwise, I'll hold off first until someone make the request, okay? So let's pay attention to this code, okay? Here, you can see that it looks similar to that pt3.c. I still remain the function called thread function. In fact, this thread function is your dining philosopher logic that you would assign to each thread, okay? Here, I also declare global variable called num_thread, which is gonna hold the number of philosopher, which is the second argument, okay? And then I also declare times to eat, which is how many times that you want this each philosopher to eat, which is the first argument, okay? And then I declare chopstick, okay, up to 32 chopstick, okay, which mean I'm simplify the problem for you that you don't have to dynamically create number of chopstick there. Then you can say that your limitation, the odd limitation of your program is up to 32 thread or 32 philosopher. So in that case, you have to add more logic, okay, in order to check whether you reach that maximum. You can make 32, you can change from 32 to be 64 or to be whatever number, okay? But I think I'll just pick some random number that I think large enough that people would probably normally would not run that put that many philosophers, okay? And then I also add one more variable called start, okay, which it would be it's just like a traffic light, okay, because when I create number of thread that many times, 32 times, okay, immediately once you finish create the first thread, the thread will start working, right? So in that case, I don't want all the thread to start until every thread is ready. So in that case, I will declare a global variable called start, and then I initialize to be 0. And then once I finish create that number of thread by put into that loop pthread underscore create, and then I have the loop from 0, I less than number of thread, okay? After I finish that loop, then I will reset start from 0 to be 1. And then within the dfill or thread function, I will check this status. So I will put in the loop in the thread function or dfill function, and it keeps checking, okay, until the start equal to 1, and then it will proceed to execute the main dfill function. Make sense, guys? Okay. Now let's come into the main function. The main function, okay. Normally, previous example, I don't deal with argc and argv. But in this case, from the requirement, the assignment requirement, I want you to take the argument. So in that case, you must check if number of argument. If it's not equal to 3, okay, then you print out to say invalid and then exit. You don't want to do anything. Otherwise, if it equal to 3, then you take the first argument, argv. Remember, I told you argc and argv. So standard C language, okay, normally you have empty argument main, okay, or you can have main with 2 argument. In fact, there is a variety of main that would take 0 argument, 2 argument, and 3 argument. And you can also pass environment variable into as the third arguments too, okay. But let's focus on what we have here, which is 2 argument, argc and argv. Argc represent uh, the number of argument, and argv represent a list or an array of character string, okay, which is whatever those arguments. So it come with character string, okay. So therefore, when you want to obtain argv1, which is let's say if I put d field 5 and 7, okay, 5 in fact it's not integer, is an ASCII, is a character string or ASCII. So therefore you have to call a utility called A2I. A2I is a utility that convert character string into integer. A stand for ASCII, I for integer. Then once you convert, then you can assign to time to it, okay, which is as a global variable here. And then the second argument, arg2, then you also convert number of thread, which is number of philosophers, okay, to this, okay, number of thread. So you do the same thing as A2I with argv2, second argument, okay. And then after that, then you declare a handle to the philosopher ID. Philo underscore D is ID because you want to have ID or index, okay, so that you can determine whether it's odd or even number later on. Are you guys with me? So this is the line, okay. And then after that, you declare a handle to the thread. So you do thread ID and then bracket num thread here, okay. And then also you also declare times eaten, okay, and then declare number of thread or eaten times, okay. So it's array of number of eaten, okay. Then you ready to initialize the mutex, because you have to use mutex chopstick, okay. So every time when each thread or philosopher to try to grab left and right chopstick, you have to protect because it's a shared variable, okay. The neighboring one would share to neighboring philosopher. So in that case, you have to initialize this mutex chopstick, okay. But then you declare or you go through like 10 whatever this number of time, okay, and then loop, okay. In fact, you don't have to use continue, I think this continue is just extra thing. It's gonna be the same thing without continue, okay. So you initialize mutex, okay, that for that number of thread there, okay. Then after that, you're ready to create thread, okay. So in this case, you create pthread create, okay, and then you are passing this first argument is the handle to the thread, okay. So you put ampersand sign, which is an address to, because the syntax of the argument is a pointer to the thread handle, okay. And then when you create thread, okay, then you have these thread handles, okay, passing, okay. And then you to null, which is second argument. Normally if you want to use a default behavior of this runtime, the thread scheduling, just use null. And then the next argument, okay, is a pointer to a function that you want the thread to execute, which is your default function, okay. And then the last argument is an argument to this function, okay. After that, now you notice that after this loop, all number of thread will be created. Then we will set start equal to 1, okay. That means when every thread being created, we are ready to let the thread to start thinking and eating, right? Therefore, we're gonna flip from 0 to 1. Make sense? okay, and then after the master thread create that number of thread or number of philosopher, then he will wait for all the children thread to complete by call p thread underscore join, okay, and then after you finish here you can print f to say the program complete here. It's your optional thing, don't just exactly use I'm just giving some sample code for you to at least some idea to start with, okay. Now let's take a look at the thread function. As you see that we have y start equal to 0 and do nothing. You guys remember the start, I'm using a declare global variable. It will be a traffic light indicator that once it turns green, then every thread will start working. And then we set start equal to 1 once we finish our thread creation here, okay. And then after that, then you can get the argument, okay. So this argument which you're passing is the index where you're gonna determine your logic here, whether it's odd or even number, okay. And then this sample code I didn't give you, the logic of the philosopher, because that is the crux of this program, okay, that you need to write the p-thread code with the mutual exclusion or synchronization in a way that it can avoid the deadlock, okay. So in this case, to avoid the deadlock, you don't need to create resource allocation graph, okay. All you have to do is just implement asymmetric solution where the odd number check the left, try to grab the left first with the mutex lock and unlock, and then after he can grab the left one and then go to grab the right one, and then the even number do opposite way, okay. So you add your own code here. Now let me just run this program, okay. Let me compile the program, GCC. Some of you guys, you can just compile with this, or you can compile with -l p thread, okay. Because it depends on your system. Some system GCC already recognize p thread package, but some system p thread package is optional. So in that case, you have to first make sure that your pthread is installed. Secondly, if GCC does not recognize pthread, you may want to specify -l. -l specify your library pthread that you want to use, okay. So now I'm running a.out. If I run a.out, don't put any argument, then it's gonna say invalid argument. Or when I say a.out with only one argument, it does not work, okay. In this case, let's say that I'm running with the correct number of argument 2 and 3, okay. So in this case, it's we take 2 argument and then try to do a to I and then compile and run program. All right, so I think I have a few, maybe 2 or 3 minutes left. If you guys have any question, you can type this, and if you want, I can hold back this sample code, the din1.c, but if you want me to upload, I don't mind to upload and share. Otherwise, until you guys request me, okay, then I'll share this. Otherwise, you can just follow me. In fact, I'm going through almost every line, and the main logic in terms of create number of threads is already being given. Including how to set up the mutex chopstick as well, So in that case, in the thread function, you have to have p thread mutex lock and unlock in between the chopstick. All right, okay. So otherwise, I'm hanging on this for a few minutes, okay. And you can chat, or you can, if you guys cool, okay, you can leave. Otherwise, you want me to do anything or even share this code, please make the request, okay. Otherwise, I think if you follow me, go back to see my video again, you probably see every line there. All right, guys. So have a good day. Stay safe, guys, and please make sure that you complete all assignment or activities. I'm still see maybe 1 or 2 person missing certain things like some homework, which is, I think normally it's okay, But I think during this time, I think a challenge time, I want to make sure that it's not just like you kind of slack off or don't pay attention. You may have some certain reason that you are unable to attend or do something. Let me know. I'm willing to help or working with you. Okay. Can you send email about the topic over a week before I don't reply? Okay, send Jillian, send to my naibox dot gmail, naibox dot gmail. Let me type. Okay. um don't send to tech mail. Okay. If any of you guys want my quick attention, send to naibox at gmail.com. Okay. All right, should be fine, just follow it. Okay. All right. Anyway, all right guys, so stay safe. Make sure you send the five references of your term paper. I will post. I think I thought that I already posted the topic, but I'll post on Moodle again. Okay, and if you guys want to talk to me, I think Isaac sent me email, want to meet with me at 1:30 tomorrow. I'm sorry. Normally it's my office hour, but tomorrow I'm chairing the data science initiative meeting that I'm trying to kind of round up, a moral of all these junior professor and create a new concentration, which I'm hoping in the future it could be our own department called data science. Okay, so I think I call for the meeting and everyone, all professor available from 1 to 3. So if you guys want to talk to me on Zoom, send me email. We can do anytime except 1 to 3, even weekend. I'm home. All right, guys. So stay safe, and I'll see you this coming Thursday. All right, guys. Okay.